Hello everyone, welcome to our discussion of the topic of continuity in calculus. So the basic description of or definition of continuous function is what you see on the screen now, but we will dig into more details of continuity in a bit. So let us begin with this definition. It says a function f is continuous at some number a being some interval along the x-axis, if the limit of the function as x approaches a is equal to the value of the function at a. So what you see on the left is the limit of the function as x approaches a. What you see on the right is the value of the function at a. And we've already discussed that the limit of a function at some value and the value of the function at some value are not the same thing. But when they're equal, when the limit of a function as x approaches some value is equal to the value of the function at that value, then we have what we call a continuous function. Okay, so let's more specifically, this is what we mean. More specifically, if we have the limit of the function f of x as x approaches a, if we have this limit exists, if this limit exists, number two, and of course we remember when the limit of a function at some x value, if it exists, it means that x approaching that value from left and right, the value of the function for that is equal to each other. Okay, so that's what we mean by that. And then the value of the function at a is defined. Okay, so the function at that value is defined. The function has a limit at that value. And not only these two exist or defined, they must be equal to each other. So it's possible for the limit to exist and the function to have a value at this point, but if they're not equal to each other, then the function is not continuous. So the continuity means that not only these two exist and that are defined, but they must also be equal to each other. So let's write that as the third condition for continuity. Is equal to the value of the function at that value. So three conditions for a function to be continuous. Okay. All right, so what is an example of discontinuity? Let's also have a good understanding of that. So here's an example of discontinuity, and let's show this graphically, and then we'll also discuss it symbolically. So suppose we have this graph. So here's the x-axis. And here's the y-axis, like that. And suppose we have a graph that looks like this. Suppose we have something of this type. like that. Suppose we put a hollow circle at this end. Suppose we put also a hollow circle here in the middle somewhere. And we put, let's say, a filled in circle here. And let's say that this point is, let's say that this point, at this point we have 3. And of course this, we take this function as some function f of x that has this graph. And let's also take this as, let's say, maybe 4. Okay, like that. And of course, let's right through here, let's also define that as, maybe we can call this 8. The value of function is 8 at that point. Okay. So from this graph, it is clear that this function f of x is discontinuous at what x value? Can you see it? We have discontinuity at x equals 3. Right? Right there. So let's write that down. That we have discontinuity at x equals 3. And then we ask, well, why is that? Well, first of all, you have, so because so the limit of this function, limit of f of x as x approaches x approaches 3, that is from left to right, right? When we leave it blank, if it's approaching from the left, we say 3 with a minus on top in the upper right corner. If it's approaching 3 from the right, we say 3 plus in the upper right corner. When we leave it blank like this, that means approaching 3 from both sides is equal to, what is the limit of this function as x approaches 3 from both sides? It is 4, right? It is equal to 4. From the graph, we can read that. But the value of the function at 3, so this is the limit, but, let me move this up, but the function at 3 is equal to 8. You see that? So the limit, even though it exists, it's not equal to the value of the function at 3. The limit of the function as x approaches 3 is equal to some value that is not equal to the value of the function at 3, which is 8. So therefore, 4 is not equal to 8. Therefore, the function is discontinuous at x equals 3. At x equals 3. Okay. So we define continuity. We showed an example of a discontinuous function. Let's give a few notes. These are all important notes to remember as we solve problems in the upcoming sections. So we say that a function f is continuous from the right at a number a if the limit of the function as x approaches a from the right is equal to the value of the function at a. If the limit of the function f as x approaches a from the right, let me underline that. So we're talking about continuity from the right. If that is equal to the value of the function at a. And if function f is continuous from the left, that was from the right, now this is from the left, at a, if the limit of the function f of x as x approaches a from the left is equal to, once again, the value of the function at a. Okay? So this is rather important. This is continuity from the right and continuity from the left. Like that. So we can box this as an important thing to remember. Okay. We will have a bunch of these notes. And I will post these lecture notes on Canvas or in Canvas. So you have the videos and you'll have the lecture notes. So if function f and g, so that we have two functions f and g, if they are continuous at some value a, at a, and let's see. So so there's no and here. So if these two functions are continuous at a, then I should say just then or therefore f plus g, f minus g, f times g, and f divided by g, where g is not equal to 0, are also continuous. Okay? So you remember these as the combining functions, right? From Math 124, Math 126, we talked about combining functions. So if the individual functions that are being combined are continuous, then the combined result as long as, of course, the function g is never 0, are also continuous. Let's say another note here. Polynomials are continuous for all real numbers, so that makes it easy when we deal with polynomials. So polynomials are continuous for all real numbers. Okay. Let's make a note about rational functions. Wherever the function is defined. Okay, so we do know that rational functions are undefined where the denominator is 0. So they're continuous wherever else except those points where the denominator is equal to 0. Here's a theorem. We can look at it as a note, but it's more important than a note. So it is mentioned as a theorem in your book. So if G, this is about, we talked about combining functions right now and their continuity, and now this theorem is about composite functions. So if G is continuous, function g is continuous at some value a, and function f is continuous at it's continuous at g as a function of a, then the composite function g is continuous at a. So if you have any difficulty following what this statement is saying, please review the discussion of composite functions and their domains from Math 126. Because all this is saying, it's saying that if there's some value a such that the g function at that value is continuous, then if you take the composition of f and g, the composite function is also continuous at that a value. But it goes back, this whole statement goes back to the discussion of the domain of the composite functions. It's basically saying that the composite function is continuous over the domain of the function that is being substituted in f, whatever that function is, g, h, if that function that is being embedded inside f is continuous at some value a, then the composite function f of g is also continuous at that point. Okay, and the discussion from the domain of composite function is just the backbone for this statement. So let's just mention this also symbolically. So this basically means that excuse me. And that. This next theorem is very, very important for two reasons. If you're a math major, you will see this theorem, the intermediate value theorem, again and again and again. You will see it in higher level proof-oriented classes, and you'll see it in most of your classes. If you're not a math major, the intermediate value theorem helps you understand a lot of the concepts that we talk about here in calculus. So for that, it doesn't matter what major you have, it's an important theorem to remember, and it's an easy, very easy theorem to understand and remember. So we'll talk about it now. So the intermediate value theorem does have a description, just like what we described this theorem up here. It does have a description, but before we get to that description, I want to give you a big picture idea of what it basically talks about. So let's get an understanding of this theorem before we describe it. And I'm going to do that using some graphs. So suppose we have a continuous function, right? So a function that has no discontinuities. And we like these sorts of continuous functions in calculus are very, very desirable and popular. Okay? Suppose I draw a graph that goes like that, right? And suppose we take two values along the x-axis, and we call one, let's say here, A. Basically, these 2 points are along this function, along the domain of this function. And let's take one here, right? So, and let's draw a dashed line to the curve from each of these x values, one like that, and another one like that. So basically, that point there is the value of the function at a. So f of a, and that point on the curve would be the value of the function at b. So the intermediate value theorem says, if you have a continuous function, and if you have, if you have a function that is continuous over some interval a, b, so assumption, this is the assumption of the intermediate value theorem. Assumption is that the function f of x is continuous over over the interval a to b, a comma b. If that's the case, then we must, then this is the statement behind the intermediate value theorem, we must have some number, let's call it c, some number c, in this interval between a and b such that this function, excuse me, this function does have a value at c. In other words, if the function is continuous from a to b, then we must have a value between, at least one value between a and b such that at that value the function is defined. Okay? Excuse me. Then there must be C. Then there must be C in A in this interval. We must have a C value in this interval such that f at C is equal to n. And I'm using values that your book uses. So then we must have, say, a C in the middle such that that function is defined or continuous at, at that value. So this would be the value of the function at C, that point on the curve. Okay? So this is, if you think this is an obvious statement, you are right. But it has, this kind of, this theorem has many applications when we prove other theorems in mathematics. But what other applications does it have? It has applications in locating the root of a function. So let's see how. And again, this is all about the big picture of the intermediate value theorem. So I'm sure you agree that if we have a function that is continuous between a and b over this interval, then we must have at least one value between a and b such that for that value c, the function value exists. Okay? And that's, so the intermediate value theorem works only if you have a continuous function. It does not work when you have discontinuous functions. Okay, just remember that. Here's another important application of the intermediate value theorem when we want to find the root of a function. So notice that in this graph that I drew, the value of the function from one end to the other end is always positive, right? This graph or this curve never dips below the x-axis. So at every point along this function, not only is continuous, but it's always positive. Now what happens if we have, suppose, a function that does this? Let's suppose that a function starts here. Let's say it does that, like that. So we have this continuous function once again. Let's pick some value a and b, some interval a and b. I'm just going to pick this as a and this as b. So the intermediate value theorem can also tell us this, that if you have a continuous function f of x, let's call this, so this is f of x. A function f of x, if it's continuous from a to b, and on one side it is negative, at some point if it's negative or positive, and at some point if it's negative. So if you knew the function here, we're just labeling it as some function. But if you had the function and you put in 0 for that, you would get a positive value for that function, right? So this value, this function would have a positive value at x equals 0, and it would have a negative value here. Suppose at, let's say, some quantity here, whatever that quantity, it would have a negative value, right? The function would have a negative value at that x value. So if that happens, if over some interval you have the function changing algebraic sign from positive to negative or from negative to positive, then between those two values, you must have at least one root of the function. And remember, root of the function is an x value at which the function is equal to 0. So here we have a root of that function, so root of f of x. Also here we have a root of f of x, right? So using the intermediate value theorem, we can show that if the value of the function changes at some point, maybe I should have called this, let's call this, let me call this C, or let me call this M for the sake of clarity, and let me pick this value at A. Okay, so that would be A. And the reason I made this switch is because to show that at A, this function at A has a negative value, but at B it has a positive value. So the intermediate value theorem can be used saying that if the function has a value at one end that is negative or positive, and that sign, that algebraic sign, changes at the other end, then we must have at least one root of that function between A and B, right? If we're going from negative function value to positive, or from positive to negative, it's impossible to make this transition unless we have a root, unless at some point in between the function is equal to 0, because it's at that point where the function changes algebraic sign from positive to negative and from negative to positive. Okay? This intermediate value theorem can be used to show that there must be at least one root between A and B or between M and A. At least one root, because any function can between A and B can cross the x-axis multiple times, not just once. Okay? So this was just a big picture of the intermediate value theorem. Now let's describe it. So suppose that we have some function f that is continuous on the closed interval a, b, right? And let's say n, and I'll use the same letter that your book uses in order for these to match, for my lecture notes to match what's in the book. And n is any number between function value at a and function value at b, okay, such that f of a, or such that f of a is not equal to f of b. So a and b cannot be the same value, basically. Then there must be a number c in the open interval AB such that f of c is equal to n. Okay. So let's draw a graph for this as well. And before that, I wanna box this description. Again, even if you're not a math major, it is worth your time to spend on this and make sure that you understand it, because it'll help you understand other topics in this course and the subsequent calculus courses. It's a very useful theorem in calculus. And it only applies to continuous functions. So suppose if we have this graph that does something like this. Something like that. And if we have, let's say, if we have, say, an A here, and a B here, right? So that point would be the function value at B. This would be the function value at A. If we have that at n points, then there must be a number C in between these, in between A and B. Let's say that in A and B, open interval A and B, such that the value of the function at C is defined and it's equal to some value n. Okay, so that would be f of c equals n. Okay, so all this is saying that if this continuous function exists between the interval a, b, then there must be some number in between them, let's call it c, such that for that value the function is also defined. Okay. Okay, so we've talked about several notes and theorems. Now let us work on some examples. and we want to sketch the graph of the function. So explain why why the function, I should say f of x, which is given. So we have this function, f of x is defined as 1 over x plus 2 if x is not equal to minus 2, for obvious reason, right? Minus 2 would make this undefined, and it's equal to 1 if x equals negative 2. And at the given number a. So we want to know, they're saying explain why the function f of x is discontinuous at a. A is given to us at negative 2. Okay? So it actually, even though they ask us to graph this function at the end, it's actually more helpful if we graph this first and then explain why this function is discontinuous. So let's do that. Let's graph this function first. So we have this graph. And this is a rational function, this piece of it, and we know that at x equals negative 2, we have a vertical asymptote. So let's draw that. So let's draw that. Let's draw that here. So this is negative 1, and this is negative 2, and we want to draw a dashed line to indicate that there is an asymptote, vertical asymptote, right there. And also, so x equals negative 2 is a vertical asymptote, and this is x equals negative 2, that dashed line. Also, let's find the y-intercept. So y-intercept would be wherever we have x as 0 and then y value, we should look for that. So the function at 0 would be equal to 1 over 0 plus 2, or 1 over 2, which means we have a y-intercept at 0 comma 1/2, right? So if this is 1, if this is positive 1, then 1/2 would be here. Okay, right there. So that would be 0 comma 1/2. Okay, so now we can draw this graph. So we would have a line coming from here, going through here, this point, the y-intercept, and doing like that. And here also, and also we have another piece of this graph that does like that. Like that. Okay, so that's the graph of that function. And we have the y equals 0, or the x-axis as the is the horizontal asymptote. Remember, of course, that if we learned in pre-calculus, in Math 126, that if the degree of the rational function, if the degree of the polynomial in the numerator is less than the degree of the polynomial in the denominator, in this case, the degree of the numerator is 0, the degree of the polynomial in the denominator is 1, which is less, then the horizontal or the x-axis is the horizontal asymptote. So we know that right away, okay, from Math 126. So y equals 0 is the horizontal asymptote, x equals -2 is the vertical asymptote, and that's the y-intercept. So looking at this graph then, at a equals -2, a being x value equals to -2, we can clearly see why we have discontinuity, right? Because if you take the limit of this function, as x approaches -2 from the left, if we're approaching -2 from the left, what is the limit of this function? It's -infinity, right? Right there, we know that the limit does not exist, because infinity and -infinity are not limits. And on the other side, the limit of the function as we approach a equals -2 from the right, it's +infinity. So not only the limit is not equal to each other, approaching a equals -2 from left and from right, but they're infinities. So the limit at the limit of the function as x approaches -2 does not exist. But look at this. The function at -2 is defined as 1. So I need to put a point here. At -2, according to this, we know that this piece is undefined. Let's see. At -2, right? We know this is not defined. But this piecewise function is defined such that we are told at x equals -2, the value of this function is equal to 1. So that would be a point. That point right there. So the full graph actually are these two lines for this piece, and then this dot by itself, this point by itself, which is that. Okay? So we know that the limit of the function at x equals -2 does not exist. And we know the value of the function at x equals -2 is equal to some value that is not equal to what the limit would have been. In this case, we don't even have a limit. But nonetheless, the value of the function at x equals -2 is nowhere near infinity or anything approaching that, right? So this function does not have a limit. It's not continuous at a equals -2. Therefore, it is discontinuous at a equals -2. So let us write this down symbolically. Okay, so we say because of all of this, because limit of f of x as x approaches -2 from the left is equal to -infinity, limit of the function f of x as x approaches -2 from the right is equal to +infinity, and the value of the function at -2 is equal to 1. Look at this. So therefore, from here, and from here, from all these three, the limit of f of x as x approaches negative 2 does not exist, and function f of x is discontinuous at x equals negative 2. The value of the function is nothing like the limits from the left and right, which, by the way, do not exist. The limit of the function as x approaches negative 2 from left or right does not exist. Okay? But the graph is more clear as to why we have discontinuity there. So let's do another example. So here's the function that we have this time. We have f of x equals tangent of square root of x. So we have the square root function. We have a composition of a square root function and a tangent function. Okay, so the domain of a square root is, first of all, so here's the solution. The domain of square root of x is anything positive, right? So bracket 0 comma positive infinity parenthesis. That's the domain of that piece. But the tangent function itself is not defined at it's not defined at every value, right? Because tangent function is equal to sine over cos divided by cosine, and the cosine function is not defined, or it's defined at pi over 2 and any pi multiples of that, but it is 0 at those points, which makes the tangent function undefined, right? So let's recall that. So this is one thing we need to remember. Also, we need to remember that the function or domain of tangent x, this function, is the domain is everywhere all values except, right? This is all values except the following. So this is the domain of that. X such that x is not equal to pi over 2 plus n pi, where or when n is any positive integer. Okay? So the domain of this function is bracket 0 infinity, everything positive, but the tangent function is defined everywhere except where x is equal to pi over 2 plus n pi. So pi over 2, 3 pi over 2, 5 pi over 2, and so on and so forth. Okay? So we clearly have discontinuity there, because this is defined only in positive regions. This is defined, this piece is defined everywhere except these points. So definitely we have discontinuity here. So the function, that function, that function is discontinuous when x is less than 0, right? Because when x is less than 0, then this piece is going to be undefined, so we have discontinuity, and when square root of x is equal to pi over 2 plus n pi, which means square both sides, so we get x equals pi over 2 plus n pi squared. So we have discontinuity. So this is the answer to this question, that the function is discontinuous at these points, at any x value that is negative, and also any x value for which we have that pi over 2 plus n pi, where n is, once again, n is a positive integer. So they ask us to graph this also. We can do that. So let us do that here. And we have, most of this is going to be on the positive side, so I'm going to give most of this blank space to the positive side. And I'm going to just draw vertical asymptotes for this, right? For pi over 2 plus n pi. So let's, like that. And then also we have like that. And so on. And so on, like that. All the way here. Okay, so this would be pi over 2. So x wherever is pi minus. So this, in this case, we can't go below, x cannot go below 0, right? It cannot be negative. So this is what we have in this here, like that. I'm just going to draw lines because this, where x is defined by this quantity. So I'm not going to write that down because we need to calculate that more precisely. But the graph would look like this. And like that. This is as best as I can draw these, like that. This should have been at the center here. And another one here, somewhere at the center. And this one also coming from here, going through that, and using that as the vertical asymptote. Okay, so these are the points of discontinuity. When x is less than 0, there's discontinuity. We can't have anything below that, below x equals 0, so the graph stops there. And then, of course, on the right side, wherever we have this, these are the discontinuities. Okay, just remember, these are the discontinuities. And which are these dashed red lines. Okay, like that. All right, so let's also, we talked about the intermediate value theorem. Let's do an example on that. So in this example, we want to use show that this is what we were talking about earlier when we talked about the big picture of the intermediate value theorem. This is one application we talked about. Show that there is a root of the given function, i.e., so the root of a function is where the function is 0, right? That's where the function value is equal to 0. Okay, so here's the function that we are given, and we are given third root of, or cube root of x equals 1 minus x in the interval 0, 1. So we need to use the intermediate value theorem to show that there is a root of this function in this interval. In other words, at some point between 0 and 1, function value at x equals 0 and x equals 1, we must have some x value at which this function is equal to 0. Okay, so let's do that. So first of all, here's the function. Well, let's move everything to one side and set it equal to 0. So we have a cube root of x. Let's move these two terms to the left. So we're going to have plus x minus 1. So that is the function. And then, so that would be equal to 0. So third root of x plus x minus 1 equals to 0, right? That. Okay, so you can see clearly that this function is continuous over this interval, right? Because this interval, everything here is positive, and therefore this piece is actually would be defined even x was negative, right? Because this is the third root, cube root of x. So this function is completely continuous over this interval. So let's write that down. The function f of x equals cube root of x plus x minus 1 is continuous on the closed interval bracket 0, 1 bracket, okay? Over that, we know it's continuous, which is the assumption of the necessary assumption for the intermediate value theorem to apply. If it was discontinuous, then over this interval, we could not apply the intermediate value theorem. Okay, so now let's calculate this function value at each of these endpoints. So f of x at 0 and f of x at 1. We want to calculate this function at these two endpoints. Let's do that. And we must get two values that are different in algebraic sign. Remember when we were talking about, if you rewind the video, if you don't remember it, just rewind to the discussion about the big picture of the intermediate value theorem. We talked about a graph where if you evaluate the function at some x value at one end of an interval and you get either positive or negative, and you evaluate the function at the other end of the interval over which the function is of course continuous, you're going to get another algebraic sign, let's say any opposite algebraic sign than you got at the other end. Then for sure in the middle of that interval there is a root of the function. We talked about that earlier, right? So all we have to show now is that this function has a value at 0 such that the sign, the algebraic sign of that function value is different than the function value at x equals 1. Let's show that. So at this end, if you plug that in, what do we get? We get cube root of 0 plus 0 minus 1, which is equal to 1, right? So f of 0, the function value at 0 is equal to 1. And this was at x equals 0, so now at x equals 1, which is the other end of the interval. We have the value of the function at 1, third root of 1, plus 1, minus 1, and, oh, sorry, so here, let me correct this, guys. I need to correct this. So this is not 1, but minus 1, right? So this is minus 1. And this should be also minus 1. Okay, so that's minus 1. And here we have positive 1, right? Because cube root of 1 is 1. These two cancel each other. So 1 plus 0 is just positive 1. So therefore, the function value at 1 is equal to 1. Okay? That's really what we wanted to see, because the function value at x equals 0 is negative 1. We don't care about the size of, we don't care if this is negative 5 or negative 1. All we care about that it's a negative value, and on this side it's a positive value. So we must have a value in that interval 0, 1, where at that x value the function has a root. Okay? So we have so f of, so let's see, we have, so because let's write this down. We have 0 and then minus 1, 1. So this would be root of the function, right? And on this side, what did we have? We have f of 0. And that's f of 0 is equal to negative 1. On this side, what do we have? We have f of 1 equals 1. So we must have the function equaling 0 between negative 1 and 1. It's obvious, right? Because the function is continuous. So therefore, by the intermediate value theorem, there is a number C in the interval 0, 1 such that f of C must be equal to 0, which is what I have said here. Okay? So this would be f of C. Okay? And in other words, this function, in other words, we have third root of x plus x minus 1 equals 0 has at least this is key, at least one root C in this interval 0, 1. Okay, like that. All right. So this wraps up our discussion of the continuity, and I thank you for persisting through this video. So for now, have a nice day, and I'll see you again next time.